He was one of the first people I saw present optimization at a conference, actually. So if you remember, Brett, you presented it on what was the bio something on flapping wings. I forget what the exact title was.
That's right, and I'll talk about some of that today as well.
Oh, okay, excellent. So with that, I will turn it over to you. You can get started with your talk.
Okay, are you able to see my slides?
Yes, and we can also
Okay.
hear you pretty clearly. So
Great. Okay, so yes, thanks for the introduction. My name is Brett Stanford, and I'm excited to be here today. I'm a researcher, as Abhijit said, at NASA Langley Research Center in the United States. And the title of this talk is or the subject of this talk is on topology optimization of aeronautical structures and narrow elastic structures. And I'll talk about what that means in a moment. Before I get into that, I wanted to give a brief background of where I'm coming from. I've switched to slide 2, and hopefully everyone can see a second slide here. But I work for the agency in the States, at NASA, and NASA has various centers across the United States. But we only have 4 so-called research centers, 2 in California, 1 in Ohio, and then 1 in Virginia, which is where I work at Langley Research Center. Langley Research Center is has a strong focus on aeronautics. We do other things as well, but aeronautics is a long pole in our tent. Langley is broken up into different directorates, and I work in the research directorate RD, and then the research directorate is broken up into different branches, and every branch that you think might exist probably does exist. We have a computational aerosciences branch, a materials branch, a flight dynamics branch, and so on. And I work in the aeroelasticity branch, AAB. So aeroelasticity, I'll talk about this in some detail today, and so we want to kind of go over what this means exactly. Aeroelasticity is the field where we look at interactions between structural dynamics and unsteady aerodynamics, typically for wings and airplanes, but it could be for turbine blades and rotor blades, or maybe slender bodies like missiles and launch vehicles. But the focus of today's talk will be mostly on airplanes and wings. There's a video playing now. Hopefully that video is playing adequately over the internet. And the idea here is that you have an aerodynamic flow over a wing, and that leaves behind a pressure signature. And that pressure signature is very sensitive to the shape of the wing. But the pressure signature is also a force, which is applied to an elastic body. All wings are quite flexible. And so that wing will bend and twist in response to that force. And when the wing bends and when it twists, the shape changes. And when the shape changes, the pressures change. And when the pressures change, the force changes and the wing deflects a little bit differently, and so on. So we have this give and take, this back and forth between the aerodynamics and the structural dynamics. And if the dynamic pressures are relatively low, which means we're flying relatively slowly and or at relatively high altitudes, then those two disciplines will settle into an equilibrium. They'll settle into a static aeroelastic equilibrium state. But if we're flying at relatively high dynamic pressures, say low altitudes or very high speeds, then they may not settle into an equilibrium, and which is shown in this video here. We may have an oscillatory instability, which is known as flutter, aeroelastic flutter. And we spend a ton of time in my branch, both historically and currently, studying the physics of aeroelastic flutter, and most germane for this talk today is studying how we can best design and optimize these configurations for aeroelastic flutter. So this is an overview of the branch. Historically, we're broken into 2 pieces, a numerical piece and an experimental piece. The experimental side of the branch orbits around the Transonic Dynamics Tunnel, the TDT, which is a large-scale facility for aeroelastic testing. Numerically, we do work in computational aeroelastic predictions, both low fidelity and high fidelity, and then computational aeroelastic optimization in MDO, which will be a big part of what I'll talk about today. In terms of application areas, we do work in aeronautics, looking at seeing how we can best leverage aeroelastic physics and aeroelastic optimization for the next generation of air vehicles. And then we also do quite a bit of work in rotorcraft, and then we do some work in launch vehicles as well. For the very brief amount of time those launch vehicles are in the atmosphere and subject to atmospheric loads. Okay, so with that, I'll return to my title slide. And the title of this talk was Aeroelastic Topology Optimization. So we've talked about aeroelasticity and what this means in very broad brush strokes. So I want to turn my attention to topology optimization and what this means. So topology optimization is a subset of structural optimization. Structural optimization, of course, is a subset of just numerical design optimization, numerical synthesis. So we'll start at the top, and I'll give probably some information that you guys have already heard this week, but I'll run through this quickly. But with numerical optimization, as we heard in the previous talk as well, there's three ingredients that we need: two mandatory ingredients, and one optional ingredient. The first ingredient is we need some objective function, some scalar. It's a measure of goodness, something that we want to optimize or minimize or maximize. For aircraft problems, we would want to maybe minimize weights, or minimize cost, minimize drag, minimize fuel expended, things like this. So those would be typical objective functions. The second ingredient that we need is a vector of design variables, a parameterization, a vector of design parameters. And these would be tuning knobs that the optimizer would adjust on our behalf to try and improve our objective function. So again, from an aircraft optimization problem, these could be shape variables, like which would be the optimal wingspan of our airplane. They could be structural variables, how thick should a given skin panel be, and so on. So those are the two mandatory ingredients. And the third ingredient, which is optional, is a vector of constraints. We could have an unconstrained problem, but otherwise we need a vector of constraints. Those could be equality constraints, or they could be inequality constraints. And so again, for aircraft optimization, we would have a constraint that the vehicle is trimmed, right? So lift is equal to weight. That would be an equality constraint. Or we could have inequality constraints on maneuver loads, so such that the wing does not break, right, or does not exceed a safety factor during a maneuver. In terms of optimization, there's two general families of optimization schemes: gradient-based optimization, GBO, and non-gradient-based optimization. Gradient-based optimization, as the name implies, requires that we compute derivatives. It requires that we compute the derivatives of the objective function and the constraints with respect to all of the design variables. So the derivative of the vector of constraints with respect to the vector of design variables, this is a Jacobian of sorts. Those derivatives are not always trivial to compute, and there's different options about how we can compute them, and I'll talk about this a little bit. But one way or another, we have to obtain these derivatives, and once we have them, we will start at some area of the design space, compute those derivatives, and then make some intelligent choice about the next location that we want to take a step in that design space. Recompute all of our information, all the objective functions, all the constraints, and the derivatives of all that information, take another step, and so on, and gradually make our way to the global optima. Gradually make our way to the local optima of the system. So this is how gradient-based optimization would work. For non-gradient-based optimization, there's a plethora of different types of ideas about how you could do this. But the gist of how most of them work is that we cast off a bunch of designs throughout the design space, and then we evaluate the performance of each of these designs. We don't need the derivatives necessarily, but we need to compute the objective function and the constraints. And then based on how well these designs do or do not do, we'll cast off a bunch of new designs throughout the design space, and so on. And we'll gradually sort of hunt and peck our way to the global optima of the system. So gradient-based optimization and non-gradient-based optimization, they have pros and they have cons. In my opinion, and certainly not everybody agrees with this, but in my opinion, 9 times out of 10, gradient-based optimization is your best bet. It gives you the best bang for your buck. Unless you have a problem, unless you have an optimization problem where you're going to have a messy design space or a disjointed design space, in which case you would want to use non-gradient-based optimization. Or if you have a problem where you expect to have multiple local optima, that would be an issue for a gradient-based optimizer. In that case, you would use non-gradient-based optimization. But those two issues aside, if you have a relatively clean problem and you suspect you have a single global optimum, usually gradient-based optimization is the best way forward. For problems where you have a really large number of design variables, and that's going to be a key theme of the work that I'll talk about today. For topology optimization, we could have thousands, tens of thousands, hundreds of thousands of design variables, without too much trouble. Gradient-based optimization isn't just your best bet, it's your only bet. There's no way to solve a large design optimization problem with a large number of design variables using non-gradient-based optimization. We're forced to use gradient-based optimization for those sorts of problems. Okay, so that was kind of an overview of just numerical optimization in a nutshell. Probably information you guys have already heard so far this week, and we'll continue to hear for the rest of the week. So now I wanted to drop down a level and talk about a subset of optimization, which is structural optimization. Now, structural optimization, also known as structural synthesis, has 3 categories. sizing, shape, and topology optimization. So sizing optimization is the simplest of the three. It's the one that's been around for the longest. And the idea is that you would have a truss structure of some sort, and you would ask your optimizer to find the optimal cross-sectional properties of each of those truss members in an effort to, say, minimize the mass of that structure subject to maybe stress constraints or buckling constraints or any sort of failure constraint that you might be interested in. So this would be an example of that. Maybe we would press go on our optimization and it would turn a structure that might look like this, with stiffer members all along the top and the bottom, and then a trapezoidal truss in between, for example. So this is a classic benchmark in structural optimization, which has been around for many years, a 10-bar truss, a 30-bar truss, and different benchmarks like that. This has been around for many years. The second category of structural optimization is shape optimization. So this is not quite as old, and it's not quite as easy, and it's not quite as routine. The idea here is that we would take our design domain and we would precede it with cavities, and then we would ask the optimizer to find the optimal shape of each of these cavities, which might result in a configuration like this, perhaps. So those are the first two categories. And then the third category, which is the focus of today's talk, this is a category of structural optimization, which is the newest, and I would say it's the hardest, and this is topology optimization. So topology optimization asks very, very fundamental questions about the way that our structure should look. So what should the shape of the holes be, for sure, but at a more fundamental level, how many holes do I want in the first place? Where do I want those holes to be? Should those holes be connected in some complicated way? And so on and so forth. So we're asking the topology optimization to make extremely fundamental decisions on our behalf about the way that a structure should look. So within the MDO community and the structural optimization community, topology optimization is quite the popular field. So this information is a little bit stale, but at the 2019 WSMO conference, WSMO is World Congress on Structural and Multidisciplinary Optimization. This is a fairly well-attended conference that they hold every 2 years. At the 2019 conference, there was 450 papers at this WSMO conference, and over half of those papers were just related to topology optimization. So topology optimization is quite popular within the MDO community, and those papers range from basic level research, algorithmic developments, all the way up to industrial applications and anything in between. The center of gravity for topology optimization research has always been, as far as I've been paying attention, in Denmark at DTU for reasons I've not entirely understood, but that's where it is. Those researchers have published a textbook on this topic, which is very nice and very useful. It's about 20 years old at this point, but still quite relevant. And there's a newer review article at a Wright State University, which was published about 8 years ago. In addition to these resources, there's a bunch of really nice articles that have been published over the years, educational articles that are written around MATLAB. So they're very useful for beginners. This is a classic article that came out first. It's a 99-line topology optimization code written in MATLAB, and so the paper includes the source code. And then there's been maybe, I would say, 30 or 40 different papers written since then by various research groups that are also focused around MATLAB and then target various areas of topology optimization. So articles like this are really useful. And then there's also some apps, some smartphone and tablet apps that are out there. Also a DTU product for 2-dimensional and 3-dimensional topology optimization. So there's a lot of good resources out there for people who are looking to get involved in this research topic. So in terms of solving a topology optimization problem, there's a couple different ways to do it, and I'll run through a few of them. Historically, the most popular choice for topology optimization, and the one that I use more often than any other in my presentation today, is a method called SIMP, S-I-M-P. This is called solid isotropic material with penalization. And how this works, it's relatively simple, I would say. You take your design domain and you discretize it into little pixels, into little finite elements. And then what we do is we are going to assign a design variable to every finite element. So every finite element here has its own design variable. So you can see right away that we're going to have a large number of design variables. If we have 10,000 finite elements, we have 10,000 design variables. And each design variable is going to be a binary design variable. So the optimizer is going to make a binary choice about each design variable. The design variable can be 0 or it can be 1. We'll call those design variables x sub e, where e would stand for element. And so the design variables can be 0 or the design variables can be 1. If a design variable for a given element is 0, that means we have a white element, it's void. There's no structure there. It does not contribute to the stiffness and mass of our structure. On the other hand, if the optimizer chooses 1 for a given design variable, in that case, it becomes black, it becomes solid, and then that structure does contribute to the stiffness and mass of our component. So by making this 0-1 binary choice throughout the entire design domain, the optimizer can develop some topology which could be useful to us. Now, the only problem with this, and it's a big problem with this idea, is that it's very, very difficult to solve an optimization problem with a large number of binary design variables. It's not impossible to do that, I would say, but it's quite difficult. And so historically, what has been done is that we relax this binary constraint. So rather than forcing all of these design variables to be 0 or 1, we allow them to continuously vary between 0 and 1. So now we have a design optimization problem with a large number of continuous design variables, and that falls well within the purview of gradient-based optimization. The only problem with this idea is that the optimizer is no longer trading in strict values of white or black. Right now it's wading through a design space where it could have shades of gray as well. And so the optimizer could return to us a topology with big blobs of gray throughout the design space rather than strict boundaries of black and white. And we don't want it to do that, where we wouldn't find that to be a satisfying result. And so the way that we can prevent the optimizer from returning to us design variables that have intermediate values between 0 and 1 is by, and this is the key theme of the SIMP method, is by implicitly penalizing intermediate values of x. So during the optimization process, we're going to gently nudge all of our design variables to go all the way to 0 or all the way to 1. We don't want to be too heavy-handed about it. We just want to implicitly nudge these design variables to do that. And the way that we do that is through this very simple mathematical trick here. What we do is for a given finite element, we say that the modulus, the elastic modulus inside that finite element, is given by some baseline modulus times x raised to the power p. X, you recall again, goes between 0 and 1. If it's 0, it's void. If it's 1, it's solid. And p is a power law function, typically like 3, 4, 5, something like that. So the modulus is a power law function, whereas the mass of that finite element is a linear function of x. It's a baseline mass times a linear function of x. So modulus is a power law function, and mass is a linear function. And what this very simple math has the effect of doing is that it undercuts the effectiveness, it undercuts the attractiveness in the optimizer's eyes of intermediate values of x. So the optimizer may think that a value of 1/2, which is a gray material, is an attractive value for topology because it has half the stiffness, which is not good, but it only has half the mass, and that is good. But if we use this math here with a power law function, a value of x would still have half the mass, but it would have far less than half the modulus. It would have 1/2 cubed. And so this undercuts the stiffness of an intermediate value. And so what this tells the optimizer is that if you have a design variable which you think should be less than 1, you should probably push it all the way to 0 or keep it all the way at 1. And so by implicitly penalizing these densities in this way, or implicitly penalizing these design variables in this way, we can hopefully produce in the end a 0-1 black-white solid void design. So this is an example where I'm doing this. This is an animation. Again, hopefully this is showing over the internet. And this is something that I took directly out of those MATLAB educational articles from the previous slide. So we have a cantilevered beam, which is clamped along one end. We have this force here, which is shown in blue. And the optimization problem that we're trying to solve is to minimize compliance. Minimize compliance is the same thing as maximizing stiffness. We're trying to minimize compliance under a volume constraint. So we have a 50% volume constraint here, meaning that 50% of these finite elements have got to be black and the other 50% have got to be white. So a minimum compliance optimization, topology optimization problem is a classic topology optimization benchmark. It's the optimization benchmark you'll see more than any other. So for design optimization problems where you have a strong trade-off, a strong conflict between stiffness and mass, SIMP is going to work. And when I say work, I mean it's going to return to us a topology which has mostly crisp black and white boundaries. And I found that for design optimization problems where you don't even have that strong of a conflict between stiffness and mass, SIMP still tends to work more often than not. But sometimes it doesn't work. Sometimes it'll fail and it'll return a design to you which has big blobs of gray everywhere. And so dissatisfaction with that aspect of the scheme has led to the development of alternative schemes. And I'll talk about a few of them briefly here. One of the alternative schemes to SIMP is known as a family of level set methods. And these level set methods are extremely popular in the MDO community and in the optimization community over the last 10 or 15 years. The idea of a level set method is that we have, again, we take our design domain and again, we discretize it into finite elements. And now we have this boundary or this front, which is propagating through the design domain in pseudo-time being, in our case, optimization iteration number. And the optimizer will dictate the motion of this front based on design topological sensitivities. Any element that lives behind the front is solid, and anything that lives ahead of the front is still void. And so the optimizer can push this front through the design domain in pseudo-time, and in so doing develop a topology. And the motion of this front, typically, there's various ways to do it, but a solution of the Hamilton-Jacobi equation is one popular scheme for handling that. So that's kind of a broad brush overview of level set methods. These are quite popular in the MDO community. I'm not going to talk about any level set optimization results today. A second alternative that I wanted to touch on is not nearly as popular as level set methods, but I'm going to talk about it a little bit today in my work. And this is a cellular-based method. And this is work that comes out of the University of Hawaii, maybe about 10 or 15 years ago. And the idea here is that we have a developmental program or a set of rules, which is a vector of real numbers. And these are the design variables which are exposed to the optimizer. And the set of rules, when quote unquote compiled and executed, will form the topology for us in stages via cellular division. So this set of rules tells us how to take a cell structure, and it tells us how and how often and where and when to stop subdividing the cell into smaller cells. So we'd subdivide it into 2 cells and then 4 cells and so on. This is a successive application of the rules which live in this design variable set. And then when we have our final cell structure, we can map that onto the aeronautical configuration that we care about, and then conduct optimization from there. So I'll go into a deeper dive of what this means. Again, this method is not nearly as popular as the level set method or the SIM method, but we've had good success with it for various challenging topology optimization problems. And so we'll talk about it a little bit. Okay, so I'm going to throw out my title slide one final time here. So the title of this talk was not just topology optimization, but aeroelastic topology optimization. So we talked about aeroelasticity on its own and what this may mean. We talked about topology optimization on its own and what that may mean. So we're interested in the intersection of these two fields. So there's a Venn diagram there of aeroelasticity work and topology optimization work. There's an overlap, but it's very slender. It's very small. If I go back to that same 2019 WISMO conference, which had 450 some papers, maybe one of those papers, only one, was related to aeroelastic topology optimization. So there's a community of people working inside this very small area here, but it's not that large. And the reason it's not that large is because the backgrounds necessary to be proficient in these two fields are quite different, right? So the background for aeroelasticity is quite different than the background for topology optimization, and you don't find that many people who are simultaneously interested or maybe proficient in both, perhaps. Though having said that, there are a number of important papers that have been published over the years, and I've listed a handful of them here. In addition to these papers on aeroelastic topology optimization, we will find that there are many other topology optimization papers which include optimization of aircraft structures and aircraft components, but they don't include fluid structure interactions, perhaps. So these are interesting papers, but not quite what we're after today. We'll also find a whole host of papers that look at topology optimization of fluid structure interaction situations, but not for aircraft structures. So for example, you might have a flexible filament or a flexible cantilever beam submersed in flow, right? And then you might do topology optimization within that beam. And so this is a very interesting application of topology optimization, but it's not necessarily what we're after today. We do want an aircraft focus, an aeroelastic focus. So having said all that, what are the hallmarks of an aeroelastic topology optimization problem? And I'll run through a few of them here. So first, obviously, we need some coupling between the structure and the aerodynamics, and numerically, there's various ways to handle that. And I'm not going to go into the solution details necessarily of how we could do that, but there's certainly various ways to handle the coupling of those two different disciplines. The second hallmark would be, as opposed to sort of classical conventional topology optimization, some of the physics that we're interested in here may be more complicated than what we typically see. Could be interested in unsteady physics, nonlinear physics, both on the structure and the aerodynamic side, and then eigenproblems. Aeroelastic topology optimization is rife with eigenproblem-based optimization schemes, and these are very difficult and very challenging to solve for optimization in general and topology optimization in particular. And so we'll talk about these in some detail, how we solve eigen-based optimization problems. The third hallmark is a crucial one, and this is the idea that the stiffest topology may not be the best topology, and that really runs contrary to sort of classical topology optimization. Classic topology optimization you know, the optimization objective function that we're trying to optimize is compliance. We're trying to minimize compliance. We're trying to find the stiffest possible topology, because that's typically what you want in structural optimization. For us, though, the stiffest topology may not be best, because something that's too stiff may quench beneficial aeroelastic coupling. So sometimes we want to build in more flexibility, not less, to promote aeroelastic coupling that we can take advantage of. So that's a key feature. The fourth feature that I want to talk about is this idea that the performance metrics that we care about could be aerodynamic based. Maybe we're trying to minimize drag, something like that. But the design variables are all structural, right? The topological design variables. And so the link between our output, which are our constraints in the objective function, and the input, which are the design variables, crosses over that disciplinary divide between aerodynamics and structure. And it can be very difficult for us as engineers to envision that link a priori. And that makes these sorts of problems particularly well suited for topology optimization, because we don't have to assume anything a priori about the way that the structure is going to look. The optimizer can decide for us, ideally. And then fifth and finally, we're typically going to use gradient-based optimization. As I mentioned previously, this is my preferred workflow. I won't go into the math of this really, but those gradients are going to be computed, if at all possible, using an analytical scheme, using an adjoint-based scheme. And so an adjoint-based scheme means that we can compute the derivative of a small number of outputs with respect to a really large number of inputs, namely a really large number of design variables. We can compute those derivatives exactly with a computational cost that scales very weakly with the number of design variables. And so that's very powerful for, I would say, gradient-based optimization in particular, but topology optimization as well, because we have so many design variables that we have to deal with. Okay, so I have four application areas that I want to discuss today, and these are different aeronautical configurations that we've looked at over the years and successfully applied topology optimization to them. And so we'll talk about each of these in turn. Hopefully, you'll find them useful and interesting. The first two are micro air vehicles. So these are very small airplanes. And the first category is fixed wing micro air vehicles, and the second category is flapping wing micro air vehicles. And so we'll talk about this in some detail. The categories 3 and 4 are more conventionally sized and more conventionally speeded structures. We're talking about supersonic panel flutter, and I'll talk about what that means. And then we'll also talk about wing box structures that fly subsonically for transport aircraft. So it's an entire transport wing box structure. So I'll start with this first one. These are fixed wing micro air vehicles. These are vehicles that are very small. They have a wingspan of 3, 4, 5 inches, perhaps. They have a low aspect ratio for packability reasons. And they're notoriously difficult to fly, both for autopilot and for a human pilot. Very difficult to fly due to stability issues, both longitudinal stability and lateral stability, and then also gusts. Gusts are a big problem for these vehicles because the gust speed is the same order of magnitude as the flight speed. So on gusty days, these things just get blown all over the sky. And so early on in this research endeavor, we wondered if we could build in passive shape adaptation, some aeroelastic shape adaptation into the wing to try and alleviate these issues. And so the basics of the structure are shown here. This is a top-down view of the aircraft. We have a leading edge here, which is made out of a plain weave carbon fiber, so it's relatively stiff. And then we have a central portion here with a hatch, and you pop that hatch open, and you would get into the guts of the vehicle, where there'd be like servo motors and cameras and things like that. But the rest of the wing is a latex rubber membrane skin, and embedded within that skin we have these carbon fiber batten structures. And the question we asked ourselves was, what's the optimal layout of these batten structures? And that's a topology optimization problem. What's the optimal layout? What's the optimal connectivity of those structures which are embedded within this latex rubber skin? So we conceptually designed and built and flight tested a number of different options for how those carbon fiber battens should look inside that skin, and those are shown here. So we built each one of these and we flight tested each one of these, and based on a combination of ease of manufacturability and pilot feedback, two of these designs really started to float to the surface. So the first one was this one, which I'm showing here again. So we called this a batten reinforced design, or a BR wing. And this is, we have these 3 straight battens which are immersed in the membrane skin. The leading edge attaches to our stiff leading edge, and the trailing edge goes all the way down to the bottom here. And so the trailing edge of this wing is quite flexible. And so in response to load, in response to loads, the trailing edge of this wing will deflect upwards. We'll get a negative geometric twist, and it will alleviate flight loads. And so on gusty days, this is far more stable than a nominally rigid configuration. So this is the first design that we really liked. The second design that we really liked is shown down here, and this design actually does exactly the opposite. Rather than have batten structures embedded within the membrane skin, the interior of the membrane skin is unsupported, and we have a thin strip of carbon fiber which goes along the trailing edge of the wing. So this wing, in response to loads, acts like a drum head. So in response to air loads, it inflates like a bubble or like a drum head, and it actually increases the camber of the wing, and this actually increases the loads. So these are kind of two sides to the same coin. The batten reinforced wing has load alleviation. It will decrease air loads, whereas the perimeter reinforced wing will have load augmentation. It'll actually increase the loads. So these are designs that we liked, and what we wondered to ourselves is if we could use formal numerical topology optimization to find structures which outperformed our two extremes here. If we could find that the optimal topology of the carbon fiber structure embedded within that membrane skin, which would outperform these two designs. And so the way that we did this is shown here. We have a top-down view of the vehicle again. We have this leading edge structure which remains untouched. And then we have this central portion here with the hatch. That remains untouched as well. But the remainder of the wing is our design domain. We're going to discretize this into little finite elements, into little pixels, and then we're going to use the simp idea as before. And so the simp idea means that we assign a design variable to every single finite element. So in the classical simp idea, we're going to interpolate between solid and void. Now, we don't want to do that here. We don't want any voids in our wing. So what we're going to do is we're going to have a multi-material idea. We're going to interpolate between two different materials. Material one, when the design variable is equal to 0, is going to be this latex rubber membrane skin, this very flexible membrane skin. And material two, when the design variable is equal to 1, is going to be the much stiffer carbon fiber. And we're going to interpolate between those two extremes in some way. So this is an example where we do this. Again, this is an animation which I hope is showing over the internet. And you can see that we get, we press go on our optimization, and we get some topology which forms, anything that's black is the carbon fiber, anything that's white is the latex rubber skin. You see the change in the aeroelastic deformations over the wing and the change in the aerodynamic pressures as well that result due to the optimization process. So I'll show some results here. The first thing I'm going to show is our aeroelastic physics of the rigid wing, or a solid carbon fiber wing. So this is a solid wing. At a given angle of attack, we have a CL. We have a lift coefficient, which is listed here. We have deformations, which are relatively small because the wing is rigid, or not rigid, but the wing is solid. So the deformations are small, and we have some aerodynamic pressures down here as well. And then we examine the perimeter reinforced wing, which is one of our baseline wings. So again, we have deformations in the interior, which kind of bubble up like a drum head. And this increases the camber of the wing, and it increases the lift. So the lift here, as opposed to the lift of the perimeter reinforced wing, is somewhat higher. And then we wondered if we could use topology optimization to come up with the design which outperforms this design. So we wanted to see if we could come up with a design which had even more load augmentation than the perimeter reinforced wing. So the optimization objective function in this case was to maximize the lift coefficient. And the result we get when we do that is shown here. So we have some somewhat more complicated topology, which is shown down here, and then the lift coefficient is indeed higher than our baseline perimeter reinforced wing. And then we wanted to go in the opposite direction. So then we looked at the batten reinforced wing, which is shown here. Now we don't have, bubbling up or drumhead cambering so much. We have kind of adaptive washout along the trailing edge due to the flexibility there. This washes out the load, and at a given angle of attack, the CL is quite a bit lower than the solid counterpart. It goes down to 0.777. And then we wanted to know if we could use topology optimization to come up with a design that had even more load alleviation than our batten reinforced wing. So now the objective function was to minimize the lift coefficient. Previously, the objective function had been to maximize. Now we want to go in the opposite direction and see if we can minimize the lift coefficient. And the design we come up with when we do that is shown here. This is quite a complicated topology, and I'll talk about more in a minute what it means. But indeed, the lift coefficient is somewhat lower. So the final step that we wanted to do was to actually build and test a few of these optimal topologies. So build them and test them in a closed loop wind tunnel and make sure that they were performing in the way that we wanted them to do. So we have 6 different designs down here. We've got our solid wing in black. We have our batten reinforced wing in red, and our perimeter reinforced wing in blue. And I'm showing data of lift, drag, and pitching moment as a function of angle of attack. This is experimental data. This is not numerical data. This is experimental data from a closed loop wind tunnel. The first design we wanted to optimize was this design shown here in green. This is the design which we tried to minimize CL alpha. So we wanted to minimize the slope of the lift curve, which we think is a good surrogate for trying to build in as much gust rejection as possible into our structure. So we designed this, we built it. I have a picture of it in the wind tunnel shown here. And then the green line here is shown here. And you see this green line does indeed have a shallower lift curve slope than our 3 reference lines. So we were designing this wing to minimize CL alpha. When we tested it, we did find that it had a lower CL alpha than our 3 baseline wings. The next exercise is shown here, this yellow design. This is a design where we tried to minimize the drag coefficient. So we built this, we tested it, and I'm plotting the drag coefficient results here. This yellow line does indeed have lower drag than our 3 baseline structures. And then the final exercise was shown here, this purple design where we're trying to minimize the pitching moment slope. So we want to have as negative a pitching moment slope as we can get, and this is a good surrogate for static stability. And indeed, when we plot those results here, it does have a steeper pitching moment slope than the 3 baselines. So the experimental data bears out what we're trying to do. The only problem with this work is that the optimizer for our 3 optimal designs here and the optimal designs I showed on the previous chart always prefers these 2-dimensional carbon fiber structures that are sort of disconnected from one another. They're not connected to the rest of the structure. As you can see, we have these sort of disconnected islands of carbon fiber sort of embedded within the membrane skin or floating in the membrane skin. From an aeroelastic standpoint, we know that this outperforms thin connected skeletal structures like this, right? So, and the experimental data bears that out, but they're far harder to build and far harder to maintain than a monolithic structure like that. So there's a strong trade-off there, and I'll get back to that in a moment. Okay, so that was the first part of the presentation was looking at fixed wing and MEVs. The second part of the presentation, I want to switch to my second application area, which is looking at flapping wing MAVs. So flapping wing MAV design is very much an open research problem. How best to do this is extremely challenging, I would say, far more so than fixed wing. In terms of flapping wing design, we have 3 different design choices that we have to make, and each one of them is extremely challenging on its own right. The first design choice is the actuator source. Where should our actuation come from? There's all sorts of different choices we would have to make there, and it's not really the focus of today's talk. This would be the input to the system, and then the output from the system would be the wing. We have all sorts of different design choices we make for the wing, right? So what should the shape of the wing be, the stiffness distribution, and we could use topology optimization just like in the previous couple slides, and we will do that in a moment. But the core focus of the next couple slides is in this connective tissue between the actuation source and the wing, which is the mechanism itself. So this is a drive mechanism which is going to flap these wings up and down in response to the actuation source. So here we make choices. Historically, these designs have looked like multi-jointed mechanisms, like a 4-bar linkage or a crank slide or something like that. So drive mechanisms for flapping wing MEVs, it's very challenging to do this. We have competing weight and power and authority and life cycle requirements. These mechanisms have to provide the required flapping kinematics to trim the vehicle out, but the onboard energy budget, I would say, is quite low. Furthermore, they really can't weigh that much, but they have to be sturdy enough for long life and low friction and so on. So there's been some speculation in the literature for many years now that a compliant mechanism, a flexible compliant mechanism, may be superior to the multi-jointed mechanisms at smaller scales, and the reasons for that are listed here. Assembly, tolerance, friction, and a flexible compliant mechanism is biologically inspired as well, and that doesn't necessarily help us in any concrete way, but it can't hurt either. So we wondered, as is typical, if we could use topology optimization to develop a compliant flapping wing mechanism that can best, flap 2 wings up and down in an aerodynamically optimal way. And so the design setup that we have is shown here. We have a design domain, which is shown by this square block, which is a 5 by 5 centimeter design domain. We're going to make it out of an ABS plastic. ABS is a rapid prototyping material. We have an actuation source, an applied force at the bottom here, an oscillatory force, which comes from an unspecified source. And then we have 2 wings, which are attached to the upper corners, 2 rectangular wings. And so the idea is to try and find the optimal topology inside this design domain, which will best transfer loads from the force to the wings and cause these wings to rotate up and down. And the objective function is to maximize the cycle average thrust force. So these wings are going to flap up and down. They're going to create a thrust force, which is going to be a force opposite the flow vector. What we're not doing here is optimizing the wing. So there's going to be really interesting design synergies between the mechanism design and the wing design. I'll talk about that downstream, but for now we're just holding the wing design fixed as this rectangular wing that you see here. And we're only interested in topology optimization of the compliant mechanism. So previously we were using SIMP-based ideas, but in a non-traditional way. So we were sort of interpolating between two materials because we didn't want any holes in our lifting surface wing. But here we want to use SIMP in the classic way. So we're going to interpolate between solid and void. Solid in this case being this ABS plastic, and in so doing we're going to build up an optimal distribution of topology within this design domain. So this is the first topology we came up with. Again, this is an animation, and again, I hope that it shows over the internet. What this is an optimal compliant flapping mechanism. We have an oscillating force at the bottom here, which is shown in red, and you can see this mechanism, and you can see how you can get a gist for how it works just by looking at it. We have these blue areas here shaded at the bottom. These are the boundary conditions, and I'll talk more about that in a minute. And you can see how this mechanism causes these wings to flap up and down. The red shading here shows the aerodynamic loads which develop over the wing, and the blue shading on the other side shows the inertial loads which develop over the wing. And the inertial loads are quite small. I had to scale them up by a factor of 3 so you could see them. So for this type of flight, which is sort of an ornithopter sort of forward flight mechanism, the aerodynamic loads are much larger than the inertial loads, and that is pretty typical. So this is a topology that we get, and it's quite a pixelated topology, as you can see. This is a topology that we get from when we set the volume fraction equal to 17%, meaning that 17% of our finite elements can be solid and the rest are void. And we also have a design constraint on the input motion of our force. That this input motion cannot be more than plus or minus 2 millimeters. We know from experience and from the compliant mechanism literature that if you don't put a constraint on this, the optimization problem becomes unbounded. And we can also change this constraint if we wanted, though I won't show that today, but we can change this constraint if we wanted as a good surrogate for trying to limit the stresses that develop inside these mechanisms. So this topology is quite delicate, and it's quite complicated in the way that it works. We ran a second topology, which is shown on the bottom here, but at a higher volume fraction of 30%. So now we have more of a simple mechanism, I would say here. Now, the way that this mechanism works is completely opposite of the way that the top mechanism works. If you look closely at this animation, you see that the force vectors, the red lines here, are exactly the same, top and bottom. But the way that the wing moves is exactly the opposite. So on the bottom mechanism here, a positive force causes a positive wing deflection, but for the mechanism on the top, the opposite is true. So the way that the topology operates is completely different between the two. So this topology on the bottom here, we thought was quite successful, and so we took this design, we post-processed it, we depixelated all the edges, and we put it into CAD, and we built this in a rapid prototyping machine, and then we tested it under a variety of static and dynamic loads. So this worked out quite well. One of the things that really biases these designs is the placement of this boundary condition in the lower corner here. And I have kind of a zoomed in view. We have our force here, but we have this boundary condition here, and we prescribe where that boundary condition lives, and that has an enormous impact on the way that the subsequent topology looks and behaves. And it turns out in topology optimization, we don't necessarily have to do this. We can ask the optimizer not only to decide what the topology should look like, but also decide where the boundary condition should be on our behalf. And so the way that we can do this is we attach springs to the four corners of every single finite element. So every finite element has these 8 springs attached to it. And these spring values can take on one of 2 values. The stiffness values can be 0, which means they're not there, or they can be some really large stiffness value. We'll call it K big. And K big is so large that these springs basically become rigid, and this finite element basically becomes a boundary condition. So these are design variables. These springs are design variables. And so rather than have a single design variable per finite element, now we have 2 design variables per finite element. We have the topological design variable, should this be solid or void? And we also have the spring design variable, which means the springs attached here, should they be 0 or should they be K big? And we're going to use the exact same SIMP methods to drive each spring value all the way to 0 or all the way to K big. And in so doing, by making these dual choices for every single finite element, the optimizer is not going to just decide on the optimal topological distribution, but it's also going to decide on where the boundary conditions should live. So when we do that, I have another animation here. When we do that, the boundary conditions are moved from the lower corners here, which is where they used to live, up to this location really close to the wing joint, and we have a substantially simpler wing topology than we had previously. So this really worked quite well. So this is all 2-dimensional topology optimization. We also did a foray into 3-dimensional topology optimization, looking at 3-dimensional mechanisms. So previously we were carving our topology out of a square of material and looking at single flapping rotations about a single axis. Now what we want to do is we want to carve our mechanism out of a cube of material, and we want to try to control 2 flapping angles independently. So we want an up and down flapping motion, and then an attaphane feathering motion. So So that result is shown here. This is sort of a lot to look at, but the idea is that this is a symmetry plane here, and then we have, so this is only half the mechanism, the other half would be on the other side. We have three forces at the bottom. I hope this animation is showing across the internet. We have three forces at the bottom. The central force here is pumping the wing up and down in a flapping way, and then we have two anti-symmetric forces off to the side, which are out of phase with the central force, which are responsible for the out of plane feathering motion. So if the previous work we were doing was for sort of ornithopter, forward flight types of things, this would be really more geared towards insect type motions for hovering flight. We didn't take this any further in terms of post-processing, but the post-processing for this in 3 dimensions would be pretty substantial, though I would say doable, well within the bounds of the current state of the art. Okay, so I want to reach back briefly and talk about these membrane topologies that we got a few minutes ago, and for the fixed wing designs. And what we were seeing, as I mentioned previously, was the optimizer, when we did SIMP-based topology optimization for the wings, we continually saw structures where we had sort of these disconnected two-dimensional islands of carbon fiber sort of floating inside the membrane skin. And that's as opposed to a structure that looks like this, where we have a monolithic structure, a monolithic skeleton structure. So we know that these have superior aeroelastic performance to these, and we were able to show that not just numerically, but critically we were able to show it experimentally as well. But these are far easier to build and maintain. When you fly these vehicles, the membrane skin will degrade over time, and you'll have to reskin it. And when you have to reskin it, for this structure, we have maybe 9 different pieces we have to deal with. Here, we just have a single piece. This is much simpler. So what we wanted to do for not fixed wing vehicles, but for flapping wing vehicles, we wanted to look at topology optimization parameters, parameterizations that only created interconnected skeletal patterns, that only dealt with topologies that looked like this, and an interconnected monolithic topology of structure. And the way that we do this is we use this cellular-based method, which I already alluded to earlier in the presentation. And this is work by Marcelo Kobayashi. He's a professor at the University of Hawaii. And his approach is a rule-based approach. And furthermore, it's an implicit topological parameterization. So what I mean when I say that is SIMP and a method like SIMP are explicit topological parameterizations. We have our design variables, and those design variables have an explicit link to the finite element mesh. Right, so each design variable attaches to a given finite element, so it's a very explicit relationship. An implicit parameterization, on the other hand, does not have that strong of a link. There's sort of a middleman which can live between the design variables which are exposed to the optimizer and the topology itself, and this can be beneficial in some ways. So that middleman is a so-called developmental program, and we'll talk about that more in a minute. This developmental program is a vector of real numbers, which are the design variables, and that developmental program, when it's quote-unquote compiled and executed, is going to form the topology for us in stages using cellular division-based ideas. So we'll do a run-through of that here and how this works. So again, we have a developmental program. It's a set of rules. It's basically a vector of real numbers, which we expose to the optimizer. So these are the design variables, and that set of rules, when it's quote unquote compiled and executed, is going to tell us how to take a cell structure, and then after successive application of those rules, take that cell structure and subdivide it into a bunch of smaller cells. And so it'll tell us maybe to subdivide like this once, and then subdivide again into 4, and then 8, and then 16, and so on. And so this forms the topology for us in stages using cellular division. This is what's known as a MAP-L system, or a Lindemeyer map system. This is fairly well known in the biology and the biological engineering community. Once we finish with this, we take this final topology and we map it onto our structural engineering application area. For us, it's a membrane wing. So we're going to reinterpret these cell walls as carbon fiber batten structures embedded within a membrane wing, for example. And then once we have that membrane structure, we'll evaluate the aeroelastic response of that structure, the objective function and the constraints, whatever fitness that we care about. And this is a single function evaluation from beginning to end. These are the design variables, these are our division rules, and then these are the outputs, the objective function and the constraints. In order to optimize that, we wrap this into a non-gradient based optimizer called the genetic algorithm, a GA. As I mentioned previously, I prefer to never use non-gradient based optimization, but here we have no choice, because there's no way to really compute the derivative of our output with respect to our input. So we were stuck with a non-gradient based genetic algorithm, and I'll talk about a little bit about how a genetic algorithm works in a moment. But the key feature of this is that the topology, which is here, lives under the hood. It's never explicitly exposed to the optimizer. Instead, we have this middleman, which lives between the optimization design variables and the topology itself. And this can be beneficial for us. Okay, so we want to use this cellular-based method to design for flapping vehicles. We want to use the cellular method to design the flapping wing itself, as we talked about in the previous slide, in terms of the batten structure. But we also want to use it to design the flapping mechanism as well. We want to do both at the same time, in fact. So here's an example of how we would do that. We have a set of division rules, which is shown here. These are the vector of real numbers, which are our design variables, and we use these to define the wing. And so we can pretend that this set of division rules creates a cell structure that looks like this, for example. And this is just a random cell structure that we came up with. And then we can take this cell structure and we can map it onto our wing, and we get this. So hopefully you're able to visually understand how we would go from here, and we would extrapolate this into the planform shape, and you get this structure here. And so any red batten you see here is an interior cell wall here, and then we mirror that for the other wing. And I'm showing the finite element mesh for the wings as well. So we want to do wing design, and this is how we would do that. But simultaneously, we want to do mechanism design. So we take a second set of the second developmental program, a second vector of real numbers, we can concatenate it onto the first. So rather than having an n by 1 vector of design variables, we have a 2n by 1 vector of design variables. We have the mechanism developmental program, and then we have the wing developmental program. So we can say the mechanism developmental program created a cell. Let's say it looks like this. So we have a different mechanism cell than we had a wing cell. We take this mechanism cell, and this is a little bit harder to visualize. What we do is we take this cell and we squash it into a 2 by 1 rectangle, and then we mirror it about the symmetry plane. And this provides a mechanism which looks like this. So again, I'm taking this cell, I'm squashing it into a 2 by 1 rectangle, and then I mirror it, and then I get this structure here. And then any vertice which attaches to the lower corner in green, I say that's clamped, which is similar to what we did previously. Any vertice which attaches to the upper corner, I'm gonna call that blue, and I'm gonna attach it to the wing. And then I'm going to apply an oscillatory actuation force at the bottom, which comes from some unspecified source. And these wings will flap up and down, and we'll have a flow going from left to right over the page. So this is the idea. So we're going to try to use the cellular division method to simultaneously optimize the wing topology and the mechanism topology at the same time. So that's a quite ambitious task, I would say. We want to sort of ease into this gently. So what we're going to start with is just mechanism design. So we're going to take our wing, we're going to fix it to some simple wing topology, and we'll just do mechanism design to start with. And so I'm showing the results from that here. So as I mentioned previously, we're using a genetic algorithm. A genetic algorithm, the way that this works, to be brief about it, is that we have a population of designs, and then we evolve that population of designs, and it's sort of survival of the fittest. So whatever design has the most beneficial aspect to it, those are the traits of that design which have the best chance of getting propagated to the next generation. So we have a population of designs. In our case, it's about 100 designs, and we evolve that population over about 45 generations for this case. So I'm showing generation number on the x-axis. On the y-axis, I'm showing the fitness function, or the objective function, which in our case is drag. We're trying to minimize drag, which is the same thing as trying to maximize thrust. And that's the same thing we looked at previously, trying to maximize cycle average thrust. We want to pump these wings up and down fast enough and to a large enough amplitude that we maximize the thrust force generated. I've got two things that I'm plotting. In black, I'm showing the average fitness function over the entire population. So this is the average drag force over all 100 members of my population. And then in red, I'm showing the best drag force. So this is the average, and this is the best that we have across that population. So we started generation 0. You see the average performance is not that great, but there is at least one design which is better. And as we evolve this system over across the generations, the best improves, and then the average performance it doesn't exactly coalesce with the best, but it gets to a value that's relatively close. So the features of whatever this design were have propagated through the entire population. So this was just mechanism design. We were taking our wing, we were holding that fixed, and we're just doing mechanism design. And what we come up with is shown in this animation on the bottom. And again, I'm hoping that animation comes across the internet. The wing topology is quite simple here. We just have these like a batten reinforced structure, but the mechanism topology, which is what we designed up here, looks fairly complicated. And we'll talk more about this in a minute. So that was step 1, mechanism design. Step 2 was to take the wing, to take the mechanism design that we found here, to freeze it, and to just optimize the wing details. So previously we were optimizing the mechanism alone. Now we take that optimal mechanism design, we freeze it, and we optimize just the wing alone. And so you see that the best drag that we're able to come up with has dropped even a little further. And that design is shown here. So the mechanism is the same between these two, but now we have some optimal wing topology, whereas previously we had just a baseline wing topology. And the third and final step, and you can probably guess where this is going, is to optimize the mechanism and the wing simultaneously at the same time. So we start from scratch and we optimize both at the same time. And you can see when we do that, we get a fairly dramatic drop in drag relative to our previous two exercises. Drag, in fact, has gone all the way to 0, which means we basically trimmed the system out, which is just fortuitous that happened. And the result we get when we do that is shown here. Now the mechanism is quite a bit simpler than these previous two, and the wing is somewhat simpler as well. And so this is the optimal configuration in terms of mechanism and wing. And this further proves that the synergies, the design synergies between the mechanism design and the wing design are quite strong, as we would expect them to be. The final step here was sizing optimization. So I mentioned that there's 3 categories of structural optimization: shape, sizing, and topology. We've done topology. Now we want to do sizing optimization of the mechanism to get an even better configuration. So this is the optimal mechanism topology we found in the previous chart. The sizing of that was just uniform 2 millimeter by 2 millimeter cross sections throughout. If I animate the structural deformation in response to this oscillatory load at the bottom, you can see what we have here, and the color is a normalized stress. So any color you have greater than 0 means we're not obtaining the safety factor that we want. So that's a structural stress-based failure. The wings are here, but I'm not animating them just so we can fit it all into one chart. So we ran an optimization, a sizing optimization. So we fixed the topology and we ran a sizing optimization to try and bring these stresses under control and also minimize the input force. And the result we get when we do that is shown here. This is the optimal sizing distribution. So it's been beefed up, in various locations and thinned out in other locations. And the optimal vibration of that mechanism is now shown here. You see all the colors are now less than 0 as we wanted to be, and we've been able to decrease the size of the input force as well by about 30%. So this worked quite well, I would say. Okay, so that's all I have for those first 2 application areas. Let me pause there and make sure, Abhijit, can you confirm that I'm still audible?
Yes, you're coming through clearly, and we can also see all the videos that you're showing. There is absolutely no problem.
Okay, great. I'm glad to hear it. Okay, so let me continue on there. So the first 2 application areas were sort of unconventional air vehicles. These are small scale micro air vehicles. The next 2 application areas are more conventionally sized, I would say. We're going to look at a supersonic panel flutter, and I'll talk about what that means in a moment. And then the final one would be an entire wing box structure. So supersonic panel flutter, what this is we start with some conceptual high-speed vehicle, which is shown here, and this vehicle is composed of ribs and spars throughout the entire fuselage and the tail and the wing as well. So if we zoom in on the wing, you can see we have this lattice structure of ribs and spars, and this leaves behind in the skins panels. So for example, here's a skin panel here, for example. And so we want to analyze just the skin panel. This is of what's interest to us for supersonic flows, and I'll talk about why in a moment. If we want to abstract the problem down even further, which we do, we can take a further 2-dimensional slice of that panel to have just a two-dimensional structure oscillating up and down. And that would leave us with this sort of abstracted situation here, where we have a sandwich structure, which is shown here. It's clamped, it's constrained at both ends, both at the trailing edge and the leading edge, and everything ahead of that is rigid, and everything behind that is rigid and flat as well. And we have a cavity underneath. We have supersonic flow over the top surface of this panel, so the Mach number is greater than 1, and then we have some prescribed delta T, some prescribed temperature rise over the upper surface of the sandwich structure and the lower surface of the sandwich structure. And the idea is that we want to see if we can use topology optimization as normal to take this design space, which is the space inside of the sandwich structure here, and we want to discretize this design space into little finite elements, into little pixels, and then see if we can use SIMP-based ideas to find the optimal topology of the structure that will beneficially affect the failure boundaries that we typically encounter for supersonic flows. So those failure boundaries are shown here, and so I'll go into some detail about what we're looking at. What I'm showing here are the failure boundaries for a supersonic panel. On the x-axis, we have delta T, which is the temperature rise, and on the y-axis, we have dynamic pressure, which is the severity of the flow over the top surface of that panel. If we just stick to the y-axis, we travel up this y-axis, the dynamic pressure gets higher and higher. At some point, we cross over this boundary here, and this boundary is the flutter boundary. And if we go past that flutter boundary, and this is a Hopf bifurcation point, the dynamic pressures of that flow have become so large that the system loses stability. It becomes unstable. This is our air elastic flutter that I mentioned at the top of the talk. If we go past this boundary, now we're in a linearly unstable region, and we have nonlinearities which can kick in and lead to the formation of a self-sustained oscillation known as a limit cycle oscillation, LCO. So that's what happens if we move up the y-axis. If we move up the y-axis, we do this at some delta t, the flutter boundary decreases. The reason the flutter boundary decreases is because higher temperatures rather, cause compressive forces in the panel, and those compressive forces will weaken the panel and it will cause the flutter boundary to shrink. On the other hand, if we go up the x-axis, we have if we increase delta t, at some point the structure will buckle, and once it buckles, it'll kind of pop out of place there. And if we increase dynamic pressure from there, the structure can be blown back flat again. And then if we keep increasing it, we'll go into a limit cycle oscillation. So these are the three main areas that we care about. There's a fourth area here where at sufficient delta t and sufficient dynamic pressures, we can get chaotic motions and aperiodic motions, but that's not really a focus for today's work. So from a topology optimization standpoint, there's a couple of interesting things we could look at. One of them would be to find the buckling point here and try to maximize it, try to push it as far down the x-axis as we can under a mass constraint or under a volume constraint. And if we do that, this is the topology which comes out of that. We have this diagonal cross bracing, and then we have this big void in the center. The other option which we could do is we could find the flutter point, and we could maximize it. We could try to push it as far up the y-axis as possible. And if we did that, this is the design that we would come up with. So this maximizes the unheated flutter speed. And this would be a situation where we have diagonal cross bracing at the leading edge and the trailing edge, and a big lump of mass in the middle. And the big lump of mass is meant to move around the vibration frequencies of the structure. For buckling, we have no interest in vibration frequencies, but for flutter, we definitely do. And so these designs are apples to apples in the sense that they have the exact same mass, they have the exact same volume fraction. In this case, a 30% volume fraction. The buckling topology is completely symmetric left to right. The flutter topology is not symmetric left to right, and that's due to the biasing effect of the flow. So these are both eigenvalue optimization problems. Eigenvalue optimization problems are notoriously difficult to solve, especially for topology optimization, because we have such a massively large design space. This is a stationary eigenvalue problem. This is an eigenvalue tracking problem, meaning that we have to compute eigenvalues and watch how they migrate as a function of increased dynamic pressure. And we're looking for one of those eigenvalues to go from negative real part to positive real part. And when that happens, that's flutter. And so this is a much more difficult problem to solve. One of the issues that we can run into is discontinuities in the design space due to mode switching. And so where the identity of the critical mode can change during the design optimization process and lead to discontinuities in the design space. And there's various techniques that we can use to try and prevent that from happening. So if we look a little bit closer at the relationship between topology and the physics that we care about, this is a buckling optimal topology at a volume fraction of 0.2. We can rerun the optimization at a higher volume fraction, 0.25 and 0.3 and so on, and we can increase the volume fraction all the way to 0.55. And you can see how the topology changes in response to this change in the volume fraction constraint boundary. Basically, we get these diagonal members get thicker and thicker, and the wavelength of the diagonal members begins to shrink as well. We can repeat the exercise for flutter, and that's shown here. And so we do this for 0.2, and we can increase the volume fraction as well, and you can go up higher and higher and see how the flutter topology changes. And so again, the basic features of the method are unchanged. We get this cross bracing at either end, and we have a big lump of mass. But you can see here for the first time, I'm showing topologies where the SIMP method is starting to struggle. We have some blobs of gray here, for example. Here again, here's a third instance where we see it. So this is a situation where the SIMP method is providing to us a topology which has lumps, which has big blobs of gray throughout, which we really don't want to see. And the reason this is happening is because of this mode switching issue that I mentioned previously. And then the bottom here, I'm showing typical eigenvectors, typical mode shapes. This is a buckling mode shape that we see, and this is a typical flutter-based mode shape that we might see. I think I'm going to skip this chart in the interest of time, so I'll move on here. We've also looked at an extension from two-dimensional topologies to three dimensions. So this is an idea where we remove this two-dimensional slice and we go back to the original square panel, and we apply stiffeners underneath the square panel, like shown here. These are blade stiffeners, full-depth blade stiffeners. And the idea is to conduct topology optimization within the blades themselves, to try and improve some of the eigen performance of the structure, both buckling and flutter. So we're going to use SIMP-based topology optimization of the three straight blades here The outer two stiffeners are going to have the same topology for symmetry, and again, our emphasis is going to be on eigenvalue metrics, buckling and flutter, as before. So we'll start with buckling, which is the easiest one of the two. And furthermore, we start with an unstiffened panel. So this is just a square panel with no stiffeners underneath. We have in-plane loads. We have equal in-plane loads in the x direction and the y direction. And what I'm showing here is the critical eigenvalue, which is just 4, and this is some normalized value, of course. And I'm showing the critical eigenmode as well. So this is an unstiffened panel. And then on the other extreme, we can have full depth solid stiffeners under that wing. And in this case, the stiffener mass has a mass that's 30% of the panel mass. So the stiffener mass weighs 30% of what the panel mass weighs. And you see the critical eigenvalue has increased by an order of magnitude. So it's gone from 4 up to 71, and we have a commiserate change in the eigenmode as well. So the question was, can we use topology optimization inside these stiffeners to try and maximize buckling? And if we do so, we get this result here. So we have a fairly complicated distribution of topology within those stiffeners. Here we set the mass constraint to be 10%. So we want the stiffener mass to be 10% of the panel mass. Here it was 30% of the panel mass. So these stiffeners weigh 1/3 of what this does, but you can see the eigenvalue is not too much worse. So this was 71, this is only 66. So we can use topology optimization to our great benefit here when it comes to buckling in terms of getting a good buckling versus mass compromise. Then we can repeat the exercise with flutter. And so I'm showing the flutter mode for this square panel. It's got a non-dimensional dynamic pressure of 515. And then if I add stiffeners underneath, I get a non-dimensional dynamic pressure about 20 times higher. And you can see the flutter eigenmode has changed pretty substantially as well. And then, of course, finally, we use topology optimization to find the maximum flutter speed. And we get a topology which looks like this. We have a fairly complicated distribution of topology within those stiffeners. Here, the trade-off between eigenperformance and mass is not quite as good. So here we could remove up to 1/3 of the panel mass, but not have much of a degradation in the eigenvalue. Here, the degradation in the eigenvalue is worse. So this flutter eigenvalue is about half of what it is here, though the panels only weigh 1/3. So there is still some benefit to doing that, but it's not as substantial as it is for buckling. I'm going to skip that chart as well in the interest of time, and I'll move to my fourth application area, which is a subsonic transport wing box. So the reason we care about supersonic panels as opposed to subsonic transports is this. It may seem arbitrary because a wing box is a collection of panels which are all stitched together with fasteners and stiffeners and so on. And the reason we care about supersonic panels is because for supersonic airplanes, those airplanes tend to be a relatively low aspect ratio with high sweep. And the aeroelastic physics at the wing level are not that interesting because the wing doesn't deform much. But we can have panel flutter. All the ingredients are there for it, as we've seen in the previous chart. For subsonic flows, when the Mach number is less than 1, panel flutter disappears. It's not possible anymore. But the wings themselves are a much higher aspect ratio, and they're very flexible. And so we can have very interesting aeroelastic interactions at the wing level that we never see for supersonic flows. So this is why we care about what we care about: supersonic panels, but subsonic wings. So the subsonic transport research that we've done in recent years has a number of interesting design drivers. We have static maneuver loads that we care about, where you might be concerned about stresses inside the structure, and then buckling of the panels as well. We would be concerned about gust response, and then of course flutter boundary, not panel flutter, but actual wing level flutter. Your objective functions might be to minimize weight, maybe minimize drag, minimize fuel burn. Things like this is what you would care about. And then we have control surfaces along the trailing edge. I'm showing 20 of them here, which is far too many, but I'll talk about why that is in a minute. And we could use these control surfaces to alleviate loads, alleviate maneuver loads, gust loads, alleviate flutter, and things like that. It actually turns out that there's a myriad of interesting application areas for topology optimization of wing box structures, and I'll talk about a few of them here. The first one, and maybe the simplest, but maybe not, is the idea that we want to try and find the optimal layout of ribs and stiffeners inside this wing box. So this wing box just shows sort of straight, evenly spaced ribs. But what if we wanted something more complicated than that? What if we wanted, angled ribs, or ribs that were bunched together over here and further apart over here? Or what if we wanted ribs that were connected together in some way, or maybe curved ribs, right? So that's a topology optimization problem. How do we solve that? That's the first idea. The second idea the second idea sort of follows from the first idea. Once we have our layout of ribs, can we remove additional mass from those web structures by optimizing in lightning holes into the webs? And how would we do that? The third idea would be, and I'll leave it sort of intentionally vague for now, but this idea that we replace the ribs and the stiffeners with something better. And again, I'll leave it vague as to what that means, but I'll talk about that in some detail. And then the final idea, which is definitely off the beaten path relative to the rest of this presentation, but it's what's the optimal layout of control surfaces? We have 20 control surfaces drawn here. We don't want that many. So if we were to pick and choose just a few control surfaces, which is a topology optimization problem, how would we solve that problem? It's quite challenging. And there's some caveats at the bottom here. You know, it's always important to include optimal skin sizing alongside the topology optimization. So topology optimization will deal with material inside the wing box, but the skins and the sizing of those skins is an important design driver as well. So we want to make sure we include that as well. And it could be important to include the optimal shape of the wing, also the jig shape of the wing. So in terms of what's the optimal wingspan, the optimal sweep angle, the optimal twist distribution, and things like that. So I'll start with this first one. What's the optimal layout of ribs and skin stiffeners? And the way that we do this, specifically the question we're asking is, what is the optimal number and location and orientation, maybe even curvilinearity of ribs and stiffeners in the wing box? So this is a sample topology of straight members. You know, so we have some angling of the stiffeners. We have some bunching up of the ribs in one area, but much more spread out in other areas. And we can rotate the ribs as well if we want. Or we could look at curvilinear ribs and stiffeners, and that would be, you know, you see an idea of how you would do that here. Maybe this buys you something relative to the increased manufacturing costs, maybe it doesn't. So that would be the topology optimization problem. And at the same time, we want to do component sizing. So not only do we want to know how many ribs should we have, but we want to know that the optimal thickness of those ribs and the optimal thickness of the stiffeners. And we want to do jig shape optimization as well. So previously I talked about the three categories of structural optimization, shape, sizing, and topology. Here we're trying to do all three of those categories at the same time. And if we try to do that, that leaves us with what's known as an MINLP problem, which is a mixed integer nonlinear programming problem. This is a notoriously difficult to solve category of optimization problem. What it means is that we have some integer design variables. In our case, it would be how many ribs do we want? How many stiffeners do we want? That's an integer. And the rest of our design variables are continuous design variables. And furthermore, we have a large number of design variables. And so what this means is that we really can't use gradient-based optimization because we have integer design variables. But we really can't use non-gradient-based optimization either because we have too many design variables. And so the solution then is to use a bi-level optimization scheme, a nested optimization scheme. And I'll talk more about this in a moment, but at the inner loop of that bi-level scheme, we're going to use gradient-based optimization for the sizing and shape design variables, which are relatively well-defined and we have adjoint derivatives for. And in the outer loop, we use a non-gradient-based optimizer for the topology design variables. The topology design variables are not well behaved, and we have some integers. So here's the gist of how this nested optimization works. We have the outer level. We have a dedicated non-gradient-based optimizer, a global optimizer, and I'll talk about what that is in a moment. We take any design variable that we're going to solve at the non-gradient-based level, which are the topology design variables, and we optimize. And so the gist of how we do this is we identify some candidate design, we evaluate the aeroelastic response to that design, and we identify another design, and so on. We gradually just loop back and forth between here until we decide that we're done. So the magic of this is inside this box here, where we quote unquote evaluate the aeroelastic response of the topology design variables. Because what we're really doing here is dropping down to the local level, and we're gonna freeze the topology design variables, and now we're gonna optimize the shape and sizing variables that we can handle with a dedicated gradient-based optimizer. So we initialize the local variables, we evaluate the aeroelastic response, we update the variables, and we evaluate again. So we gradually sort of make our way through the design space until we converge. And once this is finished, we pop back up to the outer level. We provide the final objective function to this result here, and then we do this again. So this is extremely expensive, but it's really the only way we know of to handle simultaneous shape, sizing, and topology when those topology design variables include integer design variables. So these are some typical results we've got when we've done that. This is a design where we're trying to minimize fuel burn. Minimize fuel burn is sort of a good surrogate for minimizing drag. So what I'm showing is an exploded view of the topology. We've got the skins on the bottom, the stiffeners, the lower skin stiffeners. I've got the webs, the upper skin stiffeners, and the upper skins themselves. And the color is the component thickness. So we're optimizing the topology, how many ribs, how many stiffeners, the orientation of the ribs and the stiffeners. We're optimizing the sizing, which is given by the color here. And then we're also optimizing the shape. And this wing shape happens to have a fairly high aspect ratio and a moderate amount of sweep, among other things. On the other extreme, we can try to minimize takeoff gross weights. And this is a design which does not prioritize drag as much as it does trying to prioritize minimizing structural mass. So here you can see we have a smaller aspect ratio, more aggressive wing sweep, and then thinner members, but far more stiffeners. So the sizing of the components is quite a bit bigger. quite a bit smaller rather, but we have far more stiffeners than we had previously. So there's very strong interactions between our three different categories: sizing, shape, and topology. I'm going to skip this in the interest of time, and this. Let me skip down towards the end of the presentation. We mentioned that previously that once you find the optimal layout of ribs and spars and stiffeners, then we can try to remove even more material by optimizing in lightning holes. And this is an example where we've done that, where we're trying to optimize in lightning holes to the spar structures and the rib structures. And I'll kind of zoom in here. You can see we have fairly detailed truss-like structures inside some of our spars, and then some lightning holes inside the ribs as well. We've also done this with stiffeners, so where we take a wing box and we seed it with stiffeners, and then we try to find the optimal topology inside each stiffener. And so we get these trapezoidal structures. We do this for the entire wing, but the wing is so massive that we can only show on the slide just one of the wing sections, which is shown here in red. So we did it for the entire wing, but I'm only showing a single section here. The computational cost of doing this is really large because we have so many design variables. And so we use a global local approach to try and reduce the cost. And what the global local approach here means is that we compute aeroelastic loads at the wing level. And then we break the wing into panels. So the panels are delineated by ribs. So this is a panel, this is a panel, and so on. And we optimize the stiffener topology in each panel in parallel. So we do them all at once in parallel. We don't optimize to conversions. We only do a few topology optimization iterations. We don't want to go too far. And then we put the wing back together and we return to one. We recompute the wing level aeroelastic loads, which are going to be different now because the stiffness is all different. Then we break the wing into panels. We do a few more topology optimization iterations and so on. So this is something that worked quite well. I'm going to skip this as well. And so I'll just jump to the end here since I'm pretty much out of time. I wanted to talk about this idea, which I consider sort of the holy grail of topology optimization as applied to a wing box structure. And this is an idea where we would take a wing box structure and we would forget about ribs and stiffeners and spars and all the conventional things you see inside a wing box. Forget about all that. What we want to do is we want to take that wing box and fill it with millions upon millions of tiny little brick elements, tiny little voxels, if you will, three-dimensional elements, and then let the optimizer decide which of those elements should be solid and which of them should be void. Right? So this is very ambitious and very difficult. And two of the historical barriers to doing this, one has been the computational cost, because you just have millions of design variables and gigantic finite element models and so on. I would say that's becoming much more tractable in recent years due to advances in HPC. The other challenge is challenges related to how we can conduct an optimization like this in such a way that we can get an apples-to-apples comparison with conventional rib and stiffener designs. That, I'd say, is still quite a challenge. So there's been some progress here, various papers that have been published over the years, including one of ours. The most famous of these papers is this one here, and it's famous by virtue of the fact that the work is excellent and also by virtue of where it was published. If you look at the topologies inside of these papers, you will find topologies that look nothing like conventional rib, spar, stiffener, wing box structures. And the question is, why is that? And so the optimistic view might be because we have new design tools, right, which enable us to look at topologies which were not available when those original aircraft structures were designed. I think there's some truth to that, but the bigger truth is just the fact that there's not enough inside these papers in terms of realistic design constraints and design metrics that really guide aircraft design. And if we can get those into these papers, then we will eventually get designs that start to have some commonality with conventional rib stiffener designs. But this is very difficult to do due to the enormous computational cost. And so there's quite a bit of work still to be done there. We've done some work in recent years, not exactly for wing box structures, but looking at three-dimensional topologies of low-speed flutter models. So these are plastic flutter models that we would install inside a wind tunnel, and they're designed in such a way such that they flutter inside the envelope of that wind tunnel, and then we could use the data for computational validation. So this is work. These are wings that are cantilevered on this end. They're only about a foot long. They're made out of plastic. They're multi-material, 3D printed with two materials. The first material is a stiff, plasticky, load-bearing material, and the second material is a soft, rubbery space filler. So these are two different topologies, and you can see we have these branching structures, which are shown by in the colored branching structures. This is the stiff, plasticky, load-bearing material, and the color gives you the coordinate of the z coordinate, basically, in the vertical direction. So anywhere you see red, we have material up against the upper surface of the wing, and anywhere you see blue, we have material up against the lower surface of the OML. And anywhere where you don't see a color, we have this soft, rubbery space filler. And I can't plot that space filler, or you wouldn't be able to see it. But anyway, we were able to get these fairly complicated three-dimensional structures for this wing. And this wing is a wing that's designed to have a higher flutter frequency than this wing. So on our to-do list for the next couple of years is to actually build and test these in our wind tunnel and see how that goes. Okay, so I'm going to stop there. I'm a little over time, looks like. So I just wanted to list out, the various people that I've worked with on this over the years. And I'll stop there. And if there's time for questions, I'll be happy to entertain any.
So you started 10 minutes late, so it's fine. I mean, if you overshoot, and this is such an interesting talk that I tell this to all my instructors that please overshoot. We would like to hear more of you. So I guess the floor is open to questions. I have a few questions of, I work in CFD, so I have some questions related to the CFD. So for example, in one of your early slides, you showed flutter of a subsonic aircraft. So is there any indication on, can we know what kind of speeds are we looking at in that one? And the second question is that you also mentioned supersonic flutter. So again, what kind of speeds are we looking when you study those? And what kind of solver are you using? So this brings me to my third question. Typically, thermal solvers or structural solvers take fractions of the time that a fluid solver takes. So what kind of fluid solver do you use for your optimization? And in the later questions, you are talking about bricks or voxels. So do you foresee that the time taken by that optimization process will be similar to the time taken by fluid solver? Because fluid solver also typically use these voxels, right? So in CFD, what we do is we break down into the domain into tiny pieces, and then we solve like your structural solver, only that the domain is much larger and equations are much more involved.
Sure. Okay. Yeah, so we are leaning on for all the work in this presentation, we're leaning on low to medium fidelity aerodynamic solvers. For the wing stuff, we're leaning on sort of linear double lattice method codes, which are relatively cheap. They're not as accurate, but they do enable us to get quicker designs at the conceptual design level. So these are panel method codes that are relatively inexpensive. For the subsonic wings, we might be looking at transonic flows, so Mach 0.6, 0.7, 0.8, right? So we know that for some of the flutter mechanisms that we care about, they're really going to be driven by transonic effects that we can't properly handle. And so the idea would be to use lower fidelity tools at this level, and then try to transition to higher fidelity CFD-based codes. But none of what I'm showing here is CFD. This is all sort of lower to medium fidelity aerodynamics, and um, and um, And so for the panel, we're using what's known as piston theory. This is, again, a fairly low fidelity aerodynamic code. And again, those Mach numbers would be in the order of maybe 4, 5, 6. And again, the idea would be to use the lower fidelity aerodynamics and then for the conceptual design at the topology level, and then transition to a higher fidelity tool using CFD. But for sure, none of the stuff I've shown today is CFD based.
One last question, not regarding CFD, but if you can go back to slide 40.
Yes, I think this is one I had to skip.
No, so not this one. So there was one in which you showed a square panel, and then you were talking about this one, or maybe the next one, or maybe the results one. Yes. So when you talk about a square panel like this, and you are putting up stiffeners on the bottom, the 3 stiffeners, your boundary seems to be free. Is it, or do you also take into account the fact that this panel has to be fixed at the boundaries on your wing?
Yeah, it's fixed all along the perimeter of the square.
Okay,
It
so
appears otherwise.
that's
It's
kind
just
of
an optical illusion.
okay. So the second part of the question is that in the lower part of the images, the 3 images, your maximum flutter point seems to be concentrated towards the forward edge, and yet your design seems to have I should say trusses throughout and maybe tapering towards the end. I mean, so do you think, I feel that this is counterintuitive. I mean, is there some, or maybe I'm not from structure, so I'm making that comment.
Yeah, so you're actually you're a little backward there on how you're looking at this. I didn't do a good job of explaining this, but this is actually the trailing edge.
Oh,
So
okay,
this
okay.
I see. Actually, let me turn my pointer on. Sorry. Yeah, so where you see peak deformations here, this is towards the trailing edge, not the leading edge. But your observation is correct. Yeah, so why do we see that? Why do we see, truss structures along the leading edge portion here, but not as much towards the trailing edge? And to be honest, I really don't know the answer to that. I'm not sure. I think the stresses are quite large here, even though the deformations are small. And we typically see that in structures, where you have large deformations, the stresses aren't as large. So it's
maybe
something to do
because
with that.
it is at the leading edge, so it is taking most of the brunt of the wind that is coming on. So maybe that is.
Perhaps, yeah. Like I said, I think the stresses are quite large there, even though the deformations aren't that large. So I think that has something to do with it. But yeah, it's a good observation. We noticed that as well. And I would say it's not 100% clear why we're seeing what we're seeing.
Any other questions? Sorry, I took up most of the time for the questions.
No, not at all.
Participants, do you have any questions? No? Well, I'll leave it to Professor Gogulapati to conclude the session.
Yeah.
Thanks,
Brett,
Brett,
a lot for the talk, Brett. So one thing we usually ask is, are you available in case any of the audience have questions and want to reach you? Like, can we share your email ID, for example? What is the mode of communication you would prefer?
Yeah, for sure. You can share my NASA email. Absolutely.
Okay. And all right. So I do have a lot of questions, but I think I'll reach out to you separately because
Okay.
you know that I'm working in somewhat similar areas. You know that.
Yes, absolutely. I look forward to the conversation.
Yeah. Okay. So anybody else have any questions?
Okay, well, I don't hear any, but I appreciate the opportunity to come talk to you guys today. It's been a pleasure.
Yeah. Thanks a lot. Thanks a lot for the wonderful talk.
The pleasure is all ours, as they say it in the movies. And one last comment. I think all those fantasy talks about having an army of bees and birds is not fantasy anymore. It seems like it should be realized.
Yeah.
Yeah, it's getting closer for sure.
Yeah. So Brett, before you conclude, now that you're looking at this Bing box problem, I assume to make this into like bring the topology optimization into mainstream industry, you need to incorporate constraints which work or which gel with the manufacturing technologies available, right?
Right, that's right. Yeah, that's exactly so. That's a big challenge. And there's plenty of work being done in that area. You also need to be concerned about certification. I think there's a lot of structural technologies that exist that really aren't used on airplanes because of certification barriers. And that would definitely be an issue here because the design space is so massive. We can get such weird looking designs. So there's a couple challenges. It's one thing to say we can do this numerically. There's an entirely separate set of challenges to say here's how we actually implement it on a true aircraft. And so those are big barriers that we need to deal with for sure.
So one question I have regarding the certification is, suppose your rib looks, let's say, very unconventional, like the pictures that I'm looking at on the screen right now. They are not your conventional looking rib structures, right? No, not these ones. The ones, the supersonic panel that you were showing.
That's right.
Right. Now, but if these are internal to the wing geometry, does the certification require something from internal to the geometry, or is the certification going to involve only the wing behavior?
No, I think they're concerned here in the States anyway. They want to make sure that every ounce of that structure, any load bearing area of that structure is going to be satisfactorily safe. And so no, even though it's internal to the structure, we still have to make sure that we can prove out a certain amount of robustness and safety factors of the internal structures as well. And so this is a big challenge because, as you say, if you look at a rib today on an aircraft structure, they'll have lightning holes in it, but they won't look anything as weird as this. And so this is a big challenge. So for sure.
And I know the lightning holes also took a lot of time to come in because people were very concerned about drilling holes on weight-bearing structures.
Right.
So
yeah. Right.
Interesting. So I think this will go. Sorry, go ahead.
I was just going to say this is where we start. We start with the physics and see what we can do, right? Just from a physics standpoint, and then once we have a kind of a warm and fuzzy feeling that the physics are there, then we start to think about manufacturability and real life certification issues, and we have a ways to go with that for sure. But we have to start with the physics, I think.
Right. That I think we all agree on. And I'm curious to see where this leads because the manufacturing constraints are the key to pushing this to the industry level, I think, like the mainstream level.
That's right. And so there's work here in the States, a couple of professors I can think of off the top of my head, where you try and integrate additive manufacturing constraints into the topology optimization process directly. So not in a post-processing way, which is what we've done here, but try to integrate those manufacturing constraints, additive manufacturing constraints, immediately at the very beginning. And I think this is the way forward for sure. So a tight integration of manufacturing and design.
Nice. So do you at NASA plan to build and test these at some point?
Yeah, at the panel level, we do. So we want to
They probably
start
are.
simple.
They probably
Yes,
are.
that's right. That's right. We have done a little bit of that. So yes, we start relatively simple, and then we can prove the technology at a local level, at a small level, and then we can hopefully again this is years and years away, but we can try to migrate this to bigger structures.
Okay. But very nice direction though. Yeah.
Certainly, I appreciate it.
Very interesting. Yeah. Thanks for sharing with us.
Okay, thank you for having me.
Yeah. Thank you. So if there are no
Thanks,
other questions,
thanks.
we can conclude the session today.
Okay.
Thanks, Brett. Thanks a
Regards.
lot.
Thank you.
Yeah. Bye.
Bye. Good night. So I'll close the session now.
Yeah. Have a good night, everyone.
Okay.